I started webinar. Can you try? Oh, let's stop. I will start recording. Welcome everybody for another SHIELD webinar. And I'm going to share my screen and give some words of welcoming before passing to our guest. This is a webinar as part of our NASA Drive Center, SHIELD. I'm the PI and John Richardson in MIT is a program manager. And I have a nice animation to show what the heliosphere is. It's a bubble that engulf the planets and protect us from galactic cosmic rays. And the SHIELD Center is aiming to understand the properties of the heliosphere and how it's affect life on planets and in particular on Earth. Going back. So today we have the immense pleasure. Let me introduce Vicky before I say a couple of more words about SHIELD. But Vicky is a Daniel Linzer Distinguished University Professor of Astronomy and also director of the Center for Interdisciplinary Exploration Research in Northwestern University. She has a lot of accolades. She was awarded the Guggenheim Fellowship in 2021, the Danny Heinemann Prize jointly awarded by AAP and WIS in 2018, the Hans Bethe Prize in APS, the Maria Goupert Mayer Award by APS in 2008, the Annie Cannon Award by WIS. She's also a member of the National Academy of Science and American Academy of Science and a fellow of the American Association for Advancement of Science and APS. And today she's going to talk about her improbable path to breakthrough discoveries. Her area of research is on white dwarf neutron stars and how black holes interact in binary system and how they are formed and how they evolve and end their lives. Before I pass the baton to Vicky, I just wanted to mention that I talked already about SHIELD. We have this vision of understanding the heliosphere, the different processes that affect the heliosphere. There are a lot of questions that we still don't understand how the heliosphere work, and therefore the bubble around any other star works. Heliosphere is the bubble around stars that we have the most data. So if we don't understand how this bubble work, let alone how the bubbles around other stars work. SHIELD has lots of institutions involved. It's a center drive for 5 years and has experts in observation, theory, and modeling to try to achieve this goal to understand our own heliosphere. And this webinar is part of our outreach effort. And we have this logo of several activities that we have within the center. And in the big umbrella is to bring diverse voices to STEM, and all the way from undergrad to grad to younger researchers and people that are in space physics and heliospheric science know that we are decades behind other fields in terms of bringing diversity. So this is especially important for space science and for heliophysics. One of the efforts that we started in phase 1 that is very dear to my heart is these testimonials when we ask younger people to talk about their unusual path to come to be not just a space physicist, but an astronomers. A lot of them are in not just space physics, but astronomers. And we call that you cannot be what you can see. And if you go to our website, you just Google SHIELD Drive, NASA Center, you will see it. There is videos of each of them, and it's so candid and so heartwarming to hear their experience from being immigrants, from being the first generation students, from being gender fluid, etc. So we will revamp that in phase 2 and have more testimonials, and we will be reaching out to you. So if you're interested, please contact SHIELD Outreach or the directors of the broader impact team, that is Sanlin Buxner and Nick Ross, if you want to be involved. A lot of them were not involved in SHIELD, were just my students that I just asked, and they said, of course, we want to do it. Our next event that's scheduled are Peggy Shea in January. We might have a webinar between January and April. In March, we will come back to confirm, but we have scheduled in April, Linda Elkin-Tentel, that is leading a big mission, planetary mission. We're very excited with these two amazing scientists coming to talk to us. And don't forget that we have the coffee chats where I am not invited. This is only for emerging and early career scientists to talk in a safe environment about career, networking, without any PI, any big person, just to come in and have a safe environment to talk. So without ado, I'm going to stop sharing and pass to Vicky, the stage. And we will open later on the floor for questions.
Okay. Hi, everybody. Thank you for the invitation, Merav. It's a pleasure to be with you today. I'm going to try and share my screen now. And then
make it full screen. Yeah.
Put it in presentation mode and get rid of my controls here. Hide video panel. And there. Okay. So it's a pleasure to be with you today. I prepared, I understand this webinar is not a classic colloquium. I prepared a short set of slides, mainly at the level for graduate students or students in general. And I'm happy to take questions even during the presentation. If you have questions, just voice them. Right now, I'm just looking at my slides and I can't see you, the attendees, or even Merav. So you'll have to talk for me to understand that there is a question, okay? So I'm going to tell you basically about what a collection of us in the LIGO scientific collaboration went through a few years back, around 2015, as we, after decades and decades of work, we achieved a goal that for many of us was more of a dream than a goal, depending on what day we were going through. We were hopeful, and other days we thought it would never happen. So it's really a great pleasure to have experienced this transition and to have been in this privileged position to have opened a new field of astronomy. I'm gonna I start with this image by the way of downtown Chicago, is what you see here. And we prepared this image without this extra thing in the middle here. For the New York Times, when the discovery of the multi-messenger source was made, two neutron stars colliding, where we got both gravitational waves and electromagnetic waves from the same source. And we put a neutron star edge exactly to scale on top of downtown Chicago. We prepared it for outreach in general. And then it was a pleasure when the New York Times decided to put it up, because they had to actually show the skyline of Chicago instead of New York for a change. So my title, I think, that I shared with Merav is more not exactly what I'm showing here. It's From Stars to Einstein's Waves. And it's a reference to the fact that I started my career studying stars and how stars evolve once they are born, and especially how they evolve in binary systems. And a lot of my work in the beginning was in X-ray astrophysics. and then some radio pulsar work as a postdoc. And it was in my postdoc years where I, through a series of almost sort of non-conscious steps, I got involved in gravitational wave astrophysics work and eventually gravitational wave data analysis work. By the time the discovery came, I had been involved in this community for a little over 15 years, but a lot of people had been involved for 4 decades or so. So again, a privilege to be part of this. So I'm gonna start by reminding you that at present we have 3 gravitational wave observatories. At the time of the first discovery, we had 2. The 2 LIGO observatories, one in Louisiana and one in Washington. And a few years later, we were joined by a 3rd gravitational wave detector in Italy, a collaboration of France and Italy at the time. And it's important why we need multiple detectors. We actually all work together and we analyze our data in multiple ways, including coherently. But the measurements of the first discoveries are have been recognized as the most precise measurement ever made by humans across all of science and engineering. So a big recognition has to go to our scientists and engineers who worked on the instrument, and that's not what myself or my group has contributed to. We are more on the astrophysics, but also the direct data analysis for how we extract astrophysical information from the signals we find. So I'm going to start from the beginning. A lot of this talk and the sources we'll be talking about is black holes and neutron stars. So just to make sure we're all on the same page, to remind you that black holes and neutron stars actually form from stars. So just basic stellar astrophysics primer, gas and dust is what permeates galaxies, and out of gas and dust, stars form. And the vast majority of stars in galaxies actually have masses very similar to our sun. And the average star will go through its lifetime and consume its nuclear fuel in the center, and eventually experience a gentle death, form a planetary nebula, and form a white dwarf. And we're not going to be talking about white dwarfs today. Instead, a much smaller fraction of stars are going to be massive enough that will also go through their lifetime in a much shorter time, millions of years, of tens of millions of years, and they will experience a very impressive or explosive death, usually in a supernova, maybe a very bright supernova or a faint supernova, and form either a neutron star or a black hole. For a black hole, basically gravity wins altogether in the inner collapse of the star. Maybe some material is being shed and leaves the star, the collapsing inner core, or maybe all of the star collapses to form a black hole. In the case of a neutron star, the inner parts of the star collapses. You do have some mass ejection, considerable mass ejection possibly, but then gravity is not the ultimate winner, but instead you have matter being compressed all the way down to where you get the almost pure neutron matter, and neutron pressure basically can balance gravity. And you can get a neutron star, which in terms of its size, it's about 20 miles across. Now, before I get started with the gravitational wave story, it's important to point out that, of course, we had evidence that black holes exist in nature, and especially black holes formed from stars. We had evidence that they existed in nature from electromagnetic observations. So I'd like to summarize this evidence. The best evidence for the existence existence of black holes was coming from binaries. These were actually the kinds of systems I was studying in my PhD. X-ray sources where you might have a compact object that you cannot see being orbited by a regular star, and the star, the compact object's gravity is such that the star loses mass towards its companion, and that gas is being pulled down into the gravitational potential of the black hole. In this case, it could be a neutron star as well. And as it approaches the compact object, it forms a disk. The disk becomes extremely hot in the center, and X-rays can be emitted. Now, certain binaries have the kind of behavior that allows us to actually observe the companion to the compact object in the optical. And then we can make observations of the star and the motion of the star to figure out that it's actually moving in an orbit. We can do spectroscopic observations, understand the Doppler shifts of the lines in the spectra, and measure the mass of the compact object we cannot see. And through these kinds of mass measurements, there was widespread acceptance in the astrophysics community that black holes that you would expect to form from stars, masses of about anywhere between 5 and 15 or 20 times the mass of the sun, black holes existed in nature. And that was the most secure evidence for the existence of black holes. What about neutron stars? For neutron stars, which typical properties now we understand to be maybe 1 or 1.5 times the mass of the sun and a size just about 20 miles across, as I already indicated, we had evidence for their existence and very solid understanding for their existence from radio astronomy. The first discovery was made by Jocelyn Bell Burnell back in the late 60s when she was a graduate student. And the way they were discovered was through pulsating emission in the radio. And now we understand, and actually pretty soon after their discovery, it was understood that the only way you could explain the observations is through this hypothesis of a neutron star, which had been predicted theoretically well before the late 60s, highly magnetized neutron stars that were also rotating, and the rotation axis and the magnetic axis were misaligned, could actually act as radio lighthouses, and the radio beam would cross our line of sight periodically and give rise to these radio pulses that Jocelyn first observed and noticed in her data, data that had nothing to do with looking for pulsars, and it was all about actually looking for quasars. Now, I'm going to accelerate in the history of the field and tell you that in the late 50s, people, physicists were convinced that gravitational waves should be real, although there was no, and not just a mathematical prediction of Einstein's theory of general relativity. And there was, and even though there was no empirical evidence that gravitational waves should exist. So I'm going to take a few minutes first to give you sort of some intuition, build a little bit of intuition of what gravitational waves are. And then we'll talk about the fact that a few years, well, not a few, but a couple of decades later, we had empirical evidence that gravitational waves existed. So let me start with this question. What are gravitational waves? Well, for that, we need to first go to Isaac Newton's idea or concept of what gravity is. And in Newton's theory, gravity is basically a force that connects, it's an interactive force, an attractive force between any two masses. And it has no coupling and no connection to space around the masses. I'll be talking about space specifically. It's really the space-time that enters the whole discussion, but I'm going to be limiting myself to referring to space and specifically to two-dimensional space for ease of visualization and also presentation. So in Newton's gravity, when you have two masses, gravity demonstrates itself somehow by having an instantaneous attractive force applied between the two forces. Of course, you all know this, but I'm going to sort of proceed into some intuitive explanation for general relativity and gravitational waves. And then, of course, if you give, because of this attractive force, if you give a little kick to one of the bodies, you can have circular motion, let's say, for one body around the other body. And it's all because of this attractive force, which mentally, it's always sort of brings up the notion of a rod that connects two masses. And space-time is not affected. It's not affected by the presence of masses. It's not affected by the motion of masses. General relativity, as Einstein was developing it around 1915, comes up with a completely different approach. And one way to think about it is a geometric approach, which is I'm about to describe. A fundamental change in the thinking is that actually mass and space interact. And that if you have no mass presence, then space is unaffected and can stay flat, undisturbed. But the minute you bring a mass into space, then space will be curved, and you're going to have then the geometry being changed, and therefore masses will not be able to balance. And if there is some residual or stochastic velocity, you're going to end up, the mass will move, but it will respond to the curvature of the space around them. So the motion then becomes something that is unavoidable, and the kind of motion is unavoidable, and it's just a natural response to the curvature of space. So, and I haven't mentioned waves yet, so we're gonna go there. So motion now is a response to the curvature of space, and now if you also have that motion as you're moving your mass, the dimple in the space is now also moving along the space. And if the motion has acceleration in it, then the dimple, the disturbance in space-time, is actually now generating waves. Now, this is not straightforward intuitively, but it falls out of the equations of general relativity. And you can see that this dimple, as it moves around, it actually generates a traveling disturbance in space-time. So the dimples want to basically travel away from this kind of source. And that's what becomes a gravitational wave. And gravitational waves are basically the oscillations of space moving away from your source. So space-time ripples is what we usually refer to them, and the visual in two-dimensional space is quite intuitive. So now gravitational waves, like any other wave, carries energy. It also carries angular momentum in the case of gravitational waves. And it removes energy and angular momentum from the orbital motion of the two masses. So as gravitational waves are emitted, then the two masses are losing energy and angular momentum. So they are actually moving into and in spiral motion, and eventually their ultimate fate is a merger. So did we have any evidence for the existence of gravitational waves? Well, again, from electromagnetic astronomy, yes. And it goes back to pulsars. So one quick reference to the fact that just 7 years after the discovery of the first pulsar, Joe Taylor and his student Russell Hulse at the time discovered what is now known as the Hulse-Taylor pulsar. They discovered one pulsar, and they realized by timing the pulsar very precisely, they realized that basically it has a companion, that it moves in an orbit, and over many years of pulsar timing, all done by the Arecibo telescope, which doesn't exist anymore, they realized that the orbit is actually shrinking, and it's shrinking at a rate that is highly consistent to a very small error bar, consistent with Einstein's theory of general relativity and the fact that gravitational waves must be emitted from this kind of a system. So widely now, by the late 70s, it was accepted that now we have clear evidence for the existence of gravitational waves in nature. At the same time, in the 70s, there was a lot of development on the question of, if gravitational waves exist, how are we going to go about detecting them? So how does one go about gravitational wave detection? Well, actually, people tried in many different ways, but I'm going to focus into the one way that actually worked out eventually. So the basic idea is focused on laser interferometry. And of course, if you want to detect something, you have to understand what is the effect of whatever it is you want to detect on your surroundings. So as we said, the main effect of gravitational waves is really the disturbance of space-time around you. And this disturbance is not random, it's wave-like, and it's a very particular kind of wave. It comes in quadrupole nature and has two polarizations. So one, and I'm missing one other video. So it has two natures. One oscillation in quadrupole mode is in the plus orientation, and another second oscillation, the other fundamental polarization, is in the X orientation. And the squeezing and stretching of the space-time that's being experienced is actually this delta X normalized to the undisturbed distance of reference points in space. This normalized distance is proportional to what we refer to as the gravitational wave strain. Okay. In other words, the gravitational wave strain is the strength of the gravitational wave, the amplitude though, not the power in the gravitational wave, not the energy, but the amplitude of the oscillation. So how big is the amplitude of the oscillation basically tells you how big of a change in space you need to measure to directly detect gravitational waves. So in the early 70s, through the work of multiple groups around the world, but mostly independently, with some knowledge of a few publications from one group in the literature, from multiple groups in the literature, but not with direct communication among the groups. The idea of laser interferometry potentially being the solution to this question emerged. And that's what basically led to the building of LIGO and Virgo interferometers. So laser interferometry, I don't have to explain it, the basics, but here's a movie that shows you the fundamental sort of construction of how the gravitational wave detectors work. There is a a laser beam, its power has to be really high as we can tolerate it in the detector. It gets split through a beam splitter down two arms of the detector. And the two arms are needed because we want to be able to measure the quadruple nature of the wave. They go down the two arms, they bounce off two mirrors that are as isolated as possible from any other disturbance. They bounce back off the two mirrors, they come back, and then we study the interference pattern. And then what really we're measuring, well, before I get there, so the idea is that if there is a wave coming, let's say, perpendicular, crossing the plane of the gravitational wave detector, then these masses that otherwise are undisturbed, the mirror masses, will start responding to the oscillation because the space is responding to the gravitational wave oscillation. And they're gonna, I don't know if you can see my arms because I'm not seeing myself, but they're gonna oscillate.
Yeah, we can see it.
In this quadruple nature. So one arm will get squeezed while the other one is expanding and vice versa. Okay, that means now that the two laser beams will be off phase, and when you study the interference, you can figure out what is the motion of the two masses. Now, this sounds like we're really measuring, we're sort of measuring the length of the arms. But actually, in practice, that's not what we're really measuring. What we're really measuring is the difference through the phase difference, but what we're really measuring is the difference in flight time, okay? And I can come back to this if there are questions, but it is the subtle difference and it is an important difference. So the person really who took the laser interferometry idea and made it concrete for how really you're going to make this work is Ray Weiss. Worked closely with Kip Thorne because Ray didn't know much about the astrophysics and what kind of sources might be there and what kind of gravitational wave strains we might be expecting. So the two worked very closely, sort of early to mid 70s. And then they were joined later in the history of the project by Barry Barish, and the three of them effectively made the LIGO scientific collaboration work and the LIGO lab work, and led a community of hundreds of people to the discovery. So I should have played this other video. This is another representation of how the basic interferometer works. Of course, it's a lot more complicated and how you isolate the masses, and it's not just one beam splitter and just going through. There's multiple mirrors, and there's a lot of recycling of the laser beams inside the arms, and a lot of monitors on the interferometer in terms of monitoring all kinds of other disturbances that are, of course, affecting the interferometer. I talked about the LIGO scientific collaboration and hundreds of people. At present, this is all the institutions that are members of the collaboration. And they're not just US institutions, but they include Australia and England and Germany. And I joined the collaboration in 1998 or early 1999 as a postdoc at the CFA. And a year later, I moved to Northwestern as a junior faculty. And for about a year, the CFA had a LIGO group. I was the first astronomer to join the collaboration, and Ray would take me literally by the shoulders of my clothes and take me around to introduce me to people at the first collaboration meeting and say, meet Vicky, she's the first card-carrying astronomer to join our collaboration, and we need to figure out how to work with her. Another point I'd like to make before we go to the discovery, and I'm running out of time, is the fact that we connect to the fact that we often refer to gravitational wave signals as sounds or cosmic sounds or Einstein sounds, and just make a comment for why we do that. One is a complete coincidence, and the other is a little more physical and important. So the coincidence is that LIGO detectors being on the ground, of course, every detector has a frequency regime to which they are sensitive. So LIGO detectors are sensitive right now, the way they're built, to gravitational wave frequencies from about 10 hertz to about 500 hertz. And this is the range of frequencies that are that our ear is sensitive to if gravitational waves were sound waves. So you can take a gravitational wave signal and just convert the frequency evolution into sound frequency evolution and convert it into sound, okay? So this is just a coincidence. And so we often use it for outreach, but also the sounds from different types of gravitational wave sources sound very differently. So you can build a little bit of intuition. But more importantly, oops, I forgot Virgo. More importantly, I'll get to that point. Gravitational wave detectors are different in nature than electromagnetic detectors, in the sense that electromagnetic detectors function like our eyes and gravitational wave detectors function like our ears. So for any electromagnetic telescope, you really have to point, okay? Maybe you can make your electromagnetic telescope like an X-ray detector, you can make them sort of more of a accepting signals from all around, but we tend to shield them. And of course, optical telescopes, you have to point them, radio telescopes, you have to point them, etc. Gravitational wave detectors, you don't point, you put them somewhere, and then they can receive gravitational waves from all around. Like our ears, they can receive sound waves from all around, and for the detectors from under the earth, above, to the side, etc. There is an antenna pattern, of course, of sensitivity. And there is a plane where we are zero sensitive to gravitational waves, but overall our antenna pattern is very close to almost 4 pi. Okay, now the stretching and squeezing that we have been challenged to detect is very, very small. I'm sure you have heard that before. And the achievement, basically after 40 years of work and the ultimate detection, is down to measuring changes in space that are 10 to the minus 18 meters, okay? For many, many years and decades, no one would believe that this is at all possible. Einstein himself didn't believe it, but of course he wasn't thinking from an engineering perspective. But even as LIGO was being built and NSF was funding it, people still didn't believe this would be possible. This is the year slide repetition. I should have deleted. Eventually it became possible, and that brought us to September 2015. Where we received our first signal, which we didn't believe was real, but we received it, and through our data analysis, we could tell it was coming from a pair of black holes in orbit and ultimate merger. So let me tell you a little bit about that first signal. It looked this way. And even with the noise, we could see the gravitational wave chirp, as we call it. So down here, this is strain. This normalized change in distance in space because of the wave as a function of time. And what you see is you start down here still in the noise, but the wave emerges even visually after some cleaning, not in the raw data stream, but you can see it how the oscillation now emerges and the amplitude rises and the peaks are coming closer and closer together. And this is because the black holes are coming closer and closer together. The gravity and the disturbance is stronger, so the amplitude of the wave increases, but also the frequency is increasing because the motion of the two black holes is faster and faster as the orbit is losing energy and angular momentum. And eventually they merge, and then there is nothing, there is no motion, no acceleration anymore, and there's no generation of gravitational waves. So you end up with nothing after. It's a transient, and it lasted less than 0.2 seconds. We could roughly localize it on the sky, nothing to be proud of when it comes to astronomy localization. And the rest that's going to appear is for public outreach talks with the fireworks and everything. But in terms of its energy, I'll come back to the sound. In terms of its energy, the energy released in those 0.2 seconds was, of course, in gravitational waves, but if you just look at the amount of energy, it was 3 million times more than you would need to destroy the sun. And if you converted that energy in luminosity in light, it was 50 times brighter than all the stars in the universe. The source, by analyzing the data and the behavior of the signal, the frequency, the amplitude, the frequency evolution with time, we could tell that the source is 1 billion light years away, 1.3. So it was traveling for 1.3 billion light years, and then reached us in 2015, right at the time where our detectors were sensitive enough. And you heard how the sound sounds. If you convert it to sound, it's the chirp, frequency as a function of time, and it's chirp-like in the sense that it becomes louder and louder, and the frequency is increasing as a function of time. The waveform within the noise and the errors introduced by the noise is in perfect agreement with Einstein's theory of general relativity for the kinds of masses that we're measuring, etc. So we see no deviation from GR. So what we saw, what we think happened in connection to this system is basically this collision of black holes. And this is not an artist's impression. This is an actual numerical relativity simulation, which are very hard to do. But about 10 years before the detection, we were able to do this in the community. And you can see the solution to the metric through the collision of the two black holes, formation of a common event horizon. The waves are now propagating away, and eventually the signal stops. I'll mention briefly the one other sort of breakthrough discovery that came a couple of years later, and that's the double neutron star, the first double neutron star detection we made, which of course, since double neutron stars have matter, the collision of matter also generated electromagnetic emission. So what we observed in August 17, 2017, was both this chirp, which now looks very different. And here I'm showing you only 30 seconds, but it really lasted in our detectors for 160 seconds. So neutron stars, why is so long? Because neutron stars are much smaller than black holes in size. So they start their orbital motion, but it takes much longer until they merge because they're so much longer, smaller, and they go to much higher frequencies. So the chirp lasts much longer. And within a very short amount of time, within a couple of seconds, we also, a gamma ray burst was also detected. Now, it was a short gamma ray burst, and the coincidence of the two signals basically confirmed a 50-year-old mystery. We had hypotheses that short gamma ray bursts must be associated with neutron star mergers, but we really had no clear proof from electromagnetic observations only. It was not like the case of long gamma ray bursts where we had proof from electromagnetic observations. So this was the first proof that neutron star mergers can produce short gamma ray bursts. And we also, our electromagnetic community colleagues detected a subsequent, just a few hours later, optical emission that evolved the way it had been predicted should happen. Deneutronized matter that it was experienced radio decay, and it emitted first blue light that eventually became red light. And basically that's where you could get our process nucleosynthesis, and some of the heaviest elements are being produced. And this is, again, the first proof that we could tell we are getting our process nucleosynthesis happening. Maybe in terms of time, I'm gonna skip the gorgeous movie that NASA created. This is an artist impression and not a numerical relativity simulation. And I'm gonna mention that these two discoveries were pronounced 2 consecutive years as the breakthroughs of the year in all of science for each of those years. And where are we now? Now, 7 years later, we have discovered more than 90 gravitational wave mergers. The vast majority of them, the blue collections of points, are binary black holes. And as you can see, these are black hole masses. This is a mass axis. The x-axis means nothing. It's just the progression of the signals. Right now, we know more black holes through gravitational wave astronomy, 7 years of it, than we ever measured in terms of measuring black hole masses from electromagnetic astronomy. And we have a few neutron star mergers, the orange points here. And we also detected neutron star black hole mergers as theoretically predicted. And we keep basically expanding our reach and trying to understand how are these binary black holes forming? What does the rate of merger depends on? What do their masses depend on? We can measure spins. And we have now a set of questions that we can pursue that we had no way of pursuing in the past. So I'm gonna stop here. I realize
Vicky, that was wonderful. No, that was super, super exciting. I have a quick question, and I say that Sanlin has another question, not about the science, but my own question in terms of your trajectory. And I had the pleasure of reading your chapter in this great book that I recommend, The Sky is for Everyone. There's women astronomers talking about the trajectory. Mm-hmm. So your chapter was fascinating, but you didn't touch, you mentioned your parents were not from the academic world. And I was left wondering, and this is a question we have for a lot of our guests, who were your mentors and how, early on even in high school, going to college. This is a problem of any minority, especially if we're first generation.
Well,
who do you look for?
Yeah, so I will say my parents were not educated, high school graduate, my dad, and elementary school graduate, my mom. But my one mentor was my dad, not in academia, but he was very much into education. And the reason he didn't go to college was because of the war in Greece and the civil war in Greece. But in terms of academic, so he always pushed me towards education. In terms of academic mentors, I do remember, I remember very fondly an elementary school teacher who, by the way, I remember him telling my dad, she's really good in math, especially for a girl, she's really good in math, which at the time, nobody would take as an insult, okay? Then very influential seventh grade, a woman mathematician who was really, an impressive personality and didn't give a damn about anything. So I connected with her. There were no discussions about going to college or university, just that her personality and her no-nonsense kind of, it doesn't matter who you are, math, math is like reading and you better get it kind of attitude. And then physics, for me, because initially it was all about math in my head. I had a physics teacher in high school who really made physics click and sort of everything made sense. And that was 10th and 11th grade.
So once you enter into
university, then I had professors, my first astronomy professors, Yannis Siradakis, you don't know them, but I know Stamatis knows them, and Stavros Avgoloupis. They really shepherded me into research.
So just quick follow up on that, and then I will ask what the other question from Sanlin. But even though you had these mentors, let's say in college, the fact that there were not a lot of women, I bet, in undergrad, was a challenge, or how did you overcome it?
Yeah, so here's the thing. There were, when I entered the physics department, because in Greece, you enter into a department, we were 50, you had to know what you wanted to do. We were 50-50 women and guys in freshman year, students. But among faculty, there was not one woman professor. They were all 100% guys. It was so normal. It didn't even reach my brain that there was an issue there. And I remember thinking that, well, it's this way, but it's the old generation, and that I'm the new generation. And of course, there will be women professors in my future. And it was like my parents' generation, and my parents was, half my friends' mothers were in the house taking care of the kids. So to me, it wasn't a system. It felt like I'm part of a new generation and everything will be different. It took me a while. It was when I came to the US where I realized, oh no, progress is not really happening.
I have a personal story. When I went to undergrad, me and my sister went to physics, and we both came home, tell my dad, we're the only girls, you didn't tell us. But that's something similar story. I because of time, I want to jump into, I have more questions, but let me ask Sanlin, do you want to ask your question, or I can just read it? Sanlin is our broader impact.
Can you talk about the importance of networking?
Mentoring. Oh, I see. Sanlin has her video up.
Of networking early. Yeah, I mean, I think networking in a good sense, you know, no, if it's superficial networking and nothing else, if you don't work hard, you know, forget networking, it's not going to take you anywhere. But I think networking is important early on and all the time. And the way I view networking is if you don't network, so if you don't connect, then you don't know what opportunities exist around you. And I remember the way I figured out some things. For example, I discovered there were European scholarships for undergraduates to go and do research outside Greece, is because I decided to go to an undergraduate conference close by when my undergraduate advisors told me, don't go, you will not understand anything. And indeed, I didn't understand half of what was going on, but I found out there were scholarships for undergraduates. So you network in the sense that you don't have to connect and say, will you be my mentor? You just observe people, you listen to discussions, you keep your antennas up. And then you look for mentors in many different ways. I never walked up to anybody. I never walked up to Ray Wise and said, will you be my mentor? But I feel that Ray Wise has been a very important mentor in my life, because he kind of, you know, I learned how to serve on committees with him. I learned how to navigate the gravitational wave community through him, by watching him and by asking advice on specific things when I needed to ask advice. I don't know if I'm answering the question well.
I don't, Sanin, do you want to follow up on my I see mentorship, but I will let Sanin ask if you can. I think I don't know, in different fields, I think in astronomy is a little less than that, but I know in plasma physics when I was, or in space physics, you come into a network already formed, and you have to identify people that you can ask for certain advice or can mentor you. I found that I had to be a little proactive on not working directly saying you will be my mentor, but initiating collaborations with people that I knew are going to mentor me in some way as well.
Interesting.
So.
Yeah. And I think if you don't have, also if your advisor, I had an advisor who I loved, and you know, he taught me so many things and I greatly appreciate it. But one thing he didn't do is he didn't connect me to people. Okay, I would go to a conference with him. He would never take me to dinner with him, for me to meet people or whatever. So I learned to do my networking kind of on my own.
Right, that is an issue. We don't have a lot of time to explore that, maybe in a different time. But I think the issue of people that are coming from maybe a little different paths, how to help them to find that communities, to find it on their own, to navigate can be a little challenging. I want to open the floor if there is any last questions. We run out of time, and I don't want to. No, it was so fascinating. I loved it.
And you can either post in the Q&A or raise your hand and I can unmute you.
Vicky, until people ask, let me ask another question. If you have advice for somebody coming into field of, things that you would have done differently. I think you were very lucky and very, not just lucky, but you seized the opportunity in many ways. Reading your chapter, I could see how you open up the electromagnetic spectrum. You went to CFA in a smaller field and you open up, but maybe from, I don't know, was entrepreneurial in some way, your path.
Yeah.
But if you go back to
You're asking if I would have done something
differently, or based on
Yes.
your experience in your path, like an incoming student.
There was
that-
a time, I have to say, my PhD choices were not well informed. So at the time, what I worked on for my PhD was not a hot topic. Okay. And it was a time in the US where everybody in astronomy was really going for cosmology. And so after my PhD, there were basically no positions for X-ray astrophysics, and especially the modeling instead of data analysis. So it was a very hard time. In fact, I had senior members sort of saying, why are you even studying this? Or why are you not in Europe? Europe was the place to do my kind of work. And so I think if somebody had talked to me, I would have probably chosen a different PhD topic. It was hard. It was, I mean, I did stay in the field, but there was a little time somewhere around the end of the first postdoc where it wasn't clear it was going to work out, because gravitational waves were not popular. I mean, I was told, don't pursue gravitational waves. You're going to destroy your career. There'll never be a detection. So astronomers were not supporting gravitational waves. So I kind of did it part-time, and I did it in a sense of, hey, I don't care anymore. You know, whether it works out or not, I don't care. I could always go to industry. And so I did gravitational waves, and I was doing X-ray astrophysics at a time that neither of the two were popular.
Yeah, so super interesting. Vicky, unfortunately, we're 7 minutes past the hour, so we need to wrap it up. It was fascinating. And I know I have more questions, so I have another opportunity to talk to you over wine, perhaps.
Yes.
But it was wonderful. And we will post a recording on the web. Thank you so much for everybody that came, and looking forward for more webinars. Thank you, Vicky.
Bye.
Bye.